Hello, everyone. Thank you for the introduction and the welcome. Also, thank you for being here. I know the last session of a conference or symposium is not typically the most popular one, but I still see almost everyone here, so that's nice. Yeah, so I'm Costas Kokke. I'm with the Delft University of Technology, the Signal Processing Systems Group with Geert Leus and Richard Heustens. And my PC project is a collaboration between the TU Delft, the Nederlandse Defensie Academie, which is the Dutch Defense Academy, and TNO, which is a research institute for applied sciences. So there is some defense aspect or some defense interest to my work, but actually I have found that the defense applications of radar are some of the most generic radar applications out there. So you will actually not see anything defense related probably in my work for the entire PhD. Anyway, yeah, I'll actually use the title as a sort of an outline of what I'll be talking about. I will be starting with just introducing the concept of sensor selection, why you would want to do it, what it is. Then a brief introduction on angle of arrival estimation, because I'm not entirely sure if the entire room knows what that is or what goes into that. Introduce the two target Cramér-Rao bound, and then after that I will start talking about why we picked the two target Cramér-Rao bound, what it is a substitute for, and then I will combine the three concepts together to actually solve the problem that we have that I haven't introduced yet, so you don't know what I'm talking about. So let's get started with sensor selection. Suppose we have some array, and from that array we collect data, which we concatenate in a vector X for every timestamp, but maybe we have too many antennas to process all at once. So what we want to do is we want to turn this candidate array into a smaller array, and we can do this physically, so actually not placing certain arrays on our whatever footprint we have available, or we can do switching. And the reason you would want to do switching is because typically front ends, what you use to connect your antennas to your processors essentially, can be much more expensive than the actual antennas. So something that is somewhat common is you make a large array filled with all these antenna elements, but you will not actually connect all of them all at the same time. Another reason maybe, which is kind of a hot topic now, but something that I'm personally not looking into, is integrated sensing and communication, where you need to do some elements for one task and some elements for another. But I will leave that to, well, actually presenters of free today. So yeah, why? I mean, I think it should be kind of obvious based on what I just explained about how you could do sensor selections and what kind of applications you could do it. It obviously saves you some hardware. It saves you in processing because you just have to process less data, but also throughput. I mean, if you really have a very large array, it can be very difficult to get all that data to computers to process, especially if you're operating on higher frequencies. So just to make it a little bit formal, we had this vector X and we wanted to turn it into a vector Y. So we have a matrix phi, which we actually will not see after this slide, but I put it there for completeness, which is based on the selection vector P. The selection vector P is essentially just a binary vector, which has the same amount of elements as the candidate array. And if that vector contains a 1 at a certain position, that means that we will be selecting that array element. If it's a 0, we will not select it. Yeah, and then in general, for sensor selection problems, you have some task. So you want to minimize some cost to perform that task based on that selection vector. And you have a limit on how many sensors you actually want to select. So yeah, the cost function may depend on a lot other things as well, but in general, the sensor selection is we minimize some cost based on the selection. We want to find the selection that can optimally perform the task that we're interested in, given the limit on the amount of sensors that we can actually use. So then just a brief introduction to angle of arrival estimation. So these beams look a little weird. It's not necessarily how they would be traveling, but what I kind of want to show here is that for far array reflectors or sources or targets, whatever you want to call them, the rays are essentially arriving at the array elements in parallel. So this is the far field assumption. And then we can, based on the inter-element spacing of the candidate array, we can say, okay, if a target is at a certain angle with respect to our array, it should have, we know what the delays with which this signal is received at the different elements. We know what that is supposed to be. So then if you observe an amount of samples over an amount of candidate sensors, because for now we will still be talking about the candidate sensor and later we will be trimming it, with some amount of targets present, and we make the assumption of white Gaussian noise. We can express it as such, where we have what is called an array response A, which depends on the angle of arrival of the kth target, which we denote with the omega, for some signal which is reflected by the kth target. The signal need not necessarily be the same for every target. And then with the noise term, which we can equivalently write as that matrix product over there. Then for the Cramér-Rao bound, that is not mine. It shouldn't come as a surprise that this has been derived before. At least I don't think so. For those that don't know, the Cramér-Rao bound puts a limit on the amount of variance of an estimator, of an unbiased estimator. So it's essentially gives you some insight into the best you can do. What is the lowest variance you could theoretically achieve with a parameter estimator? Now, for multiple targets, this is what it looks like. I've dropped actually from the matrix A, I've dropped the dependency on omega. It still depends on the angles of arrivals, of course, but I think the equation is long enough as it is. And the D matrix is actually column-wise partial derivatives towards the angles of arrival from the individual array responses of the different targets. R here is a correlation matrix between the different signals as they are reflected by the targets. So some measure of how correlated these targets are, which we will be simplifying later. So, okay, the problem. I'm going to start with why worst case to target optimization. So in general, when people maybe do matched filter design or specifically mismatched filter design for radar, and they don't know much about the number of targets or the clutter, one thing that can be a very interesting metric to look at is integrated side lobe level or peak side lobe level. So all these little lobes that you see besides the main lobe in the middle would be considered side lobes. And these are kind of a measure of the, at least the biggest one you could say is kind of like the worst thing that one target's response can induce on an other target's response. So peak side lobe level is kind of equivalent to saying it's a worst case to target interference. So that's why we wanted to look at worst case to target optimization, because in general, like the problem really that we want to be looking at is we don't know the number of targets. We don't know where they are, but we want to have something that is at least not immediately going to fall apart if the number of targets or the positions changes. So yeah, because the Cramér-Rao bound doesn't have side lobes, and actually many estimation filters and algorithms nowadays also don't really produce side lobes. But the idea of side lobe suppression is still a rather attractive one. So that's why we wanted to, in this way, kind of bring that to actually an estimation method agnostic metric, if we can call it that. Then some other parts of the problem. some also a slight simplification of the problem here. First of all, we needed the selection dependent Cramér-Rao bound, which actually turns out to be not all that different from the original one. Essentially, we have the oh, it's an actual line. Oh, how do I get a pointer? the pointer? Oh, okay. Okay, I'll only get the laser. That's fine. Yeah, so this, yes, this is a matrix. Yeah, this is a matrix, a 2x2 matrix in this case, because we're looking at the two target design. Actually here for the cost function where we plug this in, we say the kth diagonal elements. Actually, the worst kth diagonal element is the one we want to be optimizing. So it's the worst case. So actually lower Cramér-Rao bound is what we want. So we maximize the Cramér-Rao bound over the two targets and all possible angles of arrival. So we have the worst case over the angles, and we have the worst case over between the two targets. Yeah, and that's still subject to that we have a limit to the amount of sensors that we can select. Let's see. Yeah, so this capital P is a matrix which simply has the selection vector P on the diagonal. So we're essentially just multiplying certain columns from D and A with zeros. So effectively removing them from the equation. And then we're still trying to minimize over our actual selection. So the best selection that optimizes the worst Cramér-Rao bound. Yeah, so we need some candidates before we can do any optimization. So, well, everyone's first step is the uniform linear array. So that's what we started with as well. And actually that is what's used for the core results of the paper. We simply select a reference on the first element, and then we implement essentially these phase delays. So actually this also tells you that we are assuming a narrow band signal, and then simply the derivative columns. So for each of the two targets. So then we can start analyzing the cost function of our problem a little bit, because it's not necessarily the most attractive one to optimize. So if we write it out, actually the Fisher information matrix elements for one of the targets, if we write that out for two targets with the selection vector, we actually notice something with the uniform linear array candidate, and that is that we can do certain substitutions. So this part here, the emission PD, becomes this Z double bar, which does not depend at all anymore on the angles of arrival. So that's already nice. And then we notice similarly for these other parts. So this part here, dPA, becomes here ZK emission, only depends on the difference of the angles of arrival of the two targets. And we see similar things for these other substitutions that we do. So overall, for the two target with a linear array candidate set, the Cramér-Rao bound only depends on the differences of the angle of arrival, which reduces the size of our problem, which is very nice. And I also want to add that this works for any linear array candidate set. It doesn't have to be uniform, but just linear. And then also we have some nice symmetry. So actually, and this was kind of to be expected, you see the same thing with side lobe levels. If you have two unit power signals, that actually they influence each other essentially in the same way. So not only do we only have to look at the delta omegas now, so the differences in angle of arrival, we also only have to look at positive differences in angle of arrival. So we've made our problem a bit smaller in that sense. Okay, but we still have this, we would still have this continuous set of delta omegas that we would have to evaluate over, which is not necessarily attractive either. So what we propose to do is to define a set of angles differences, which we have here as a D plus, so positive angle differences. And this is actually a uniform sampling of possible angle differences. So we start at a very small angle difference between the two targets, and we start at very small instead of 0 because, yeah, for 2 unit power sources to be co-located, that's always going to be the worst case. So then we're not really optimizing much useful. So we start at a small separation, and then we go all the way up to 180 with whatever step size you feel comfortable with, because actually that is going to be a large contributor to how much effort it's going to be to solve the eventual final optimization problem. Yeah, so once we have this set of possible angle differences, we can essentially make a constraint for each angle difference separately and define a bound on the bound. So we have for every possible angle difference, we have a Cramér-Rao bound, a separate Cramér-Rao bound, and then that is the one that we are going to that set of Cramér-Rao bounds is then what we're going to bound and optimize. So in some sense, you could think we have all these curves, and we're going to try to push them all down. Okay, still not the most attractive thing to solve. So we're going to take out the dependence of the angle differences. So we now have one constraint that doesn't depend on the angle differences anymore. Another auxiliary variable, I don't think terribly interesting for this talk. And then we do, well, kind of a classic trick where we apply the Schur complement, which is it's a theorem that connects the positive semi-definiteness of a matrix to actually these types of matrix or scalar inequalities, which depend on vectors and matrices. So, and the nice thing here is, and maybe I should have highlighted that before as well, but all of these Z substitutions, I don't know if you remember, but they all just depend on the matrix P once, which means that all of these Z variables are all linear in the selection variable P, which means that actually all of the constraints and the cost function are all linear in all of the optimization variables, which makes it efficiently solvable. There's still one part though that is not convex, which is the binary constraint here. But because everything is linear, one thing that has historically always been shown to has shown success is to do what is called randomized rounding. So we apply a box constraint on the vector P, where we say that all the elements need to be in between 0 and 1 inclusive. And then once we obtain the continuous values of this P tilde, we start to do randomized rounding. And for those that don't know, randomized rounding is if this produces a value after optimizing this optimization problem, which by the way is convex now, so we can just put this in CVX or whatever else you want to use. If this produces a value of, let's say, 0.9, then by the end of when we do the randomized rounding step, there's a 0.9 chance that we will round that element to 1. Similarly for other values. But actually, and I can show that with some numerical results later, this rounding is actually extremely consistent for a problem. This optimization problem very consistently gives continuous values that are extremely close to 1. and extremely close to 0. Every now and then you see values of 0.5, but we actually saw that for those values of 0.5, it just didn't matter which ones you picked. They essentially produced the same bound. So yeah, this is solvable. Again, you by the density of this set B plus will influence the complexity of this problem. So the amount of iterations that you could expect to need to converge here. So you could sample that more or less dense depending on how fast you want to go. Of course, then you make some sacrifice, maybe on yeah, accuracy of the solution, because actually this sampling is a simplification that we did, a relaxation. But like truly you would want all possible delta omegas, but then we haven't found a feasible way to solve for that. So so then I want to show some examples, because examples are fun. In this yeah, so if we just would have picked the single target Cramér-Rao bound, and we would just optimize that. I mean, this has been known for a while. You would just pick the edges of your array. So this top row here is just the result of essentially k equals 1. So capital K equals 1, just one target. And this kind of the intuition around this is kind of that the edge elements are best for the main lobe, and elements in the center are best for the side lobes. That's kind of an intuition. It's not super formal, but yeah, we see similar results here. So yeah, so the bottom rows here is the results from our optimization, which actually for these bottom 4 examples, it's all the case that you end up with the half being selected in the middle and then a quarter at each of the edges. But for those that are paying very close attention, in this bigger example that it's actually not the case, this is actually half of the amount of elements that can be selected plus 1. And then one of these edges is slightly shorter than the other. And that is something that that it's kind of a minuscule difference, but that comes from this minimal angle separation between the targets that you actually define. That is one of the input parameters essentially to the optimization problem, how you define that set B plus. If you change that minimum separation, so the set B plus, maybe instead of making it go from, I don't know, 0.1 degree to 180 degrees, you make it go from 1 degree to 180 degrees. You already know that they cannot be that close together. Then you will see that there will be actually less emphasis on elements in the middle. Actually, we don't have elements in the middle, but there will still be some elements from the edges that will be closer to the middle than if you were to do just single target optimization. Now for some numbers. So here in blue is the results of our method. I must admit, I find this comparison to be slightly silly, because of course we're plotting here on the y-axis the worst case 2 target Cramér-Rao bound, which is exactly what we're optimizing. So it shouldn't come as a surprise that that line is on the bottom. But what it does illustrate nicely is that these error bands, these shaded regions around the lines, are actually the best and worst cases from all these randomized trials that we did. And I think for these plots we did 100. And what you can see is that only for very select places, here a little bit, there's actually some variance due to the rounding. So the continuous values of our optimization problem were actually not super clear on what the optimum was. But for almost all the other cases, they are super consistent, and just one trial of randomized rounding is enough to get the optimal solution. And actually normally well, not normally maybe, but somewhat often when randomized rounding is implemented to solve these sorts of binary problems, you will see that you will do a number of randomized rounding trials because they're relatively cheap to do, and then you select the best result from them. But here, for the majority of cases, that turns out to not really be necessary. Again, in red, if you just optimize the Cramér-Rao bound for one target instead of the worst case from 2, and then just to have another comparison, which sometimes does surprisingly well, I have to admit, just picking elements at random. Yeah, that essentially leads me to conclusions. So yeah, we've formulated we've managed to formulate the worst case two-target Cramér-Rao optimization for sensor selection as a convex program using randomized rounding to obtain binary solutions. For the extensions, the big one, I think, is trying to apply this to planar arrays, because linear arrays are not super modern. And actually, for planar arrays, we found that the Cramér-Rao doesn't just depend on the angle differences, only for some planar arrays. So actually, what we're trying to figure out is what are the necessary conditions for planar arrays to also only depend on the difference of angle of arrival. The other one is that we assumed that the target reflected signals were uncorrelated and equal power. We want to see what happens if there's correlation between the targets. It will make the optimization quite a bit more challenging. But for certain applications of radar, you just cannot assume that they're completely uncorrelated. Yeah. And compare against methods that also optimize the Cramér-Rao, but for a known amount of sources. Because there's actually a lot of work on optimizing the Cramér-Rao for sensor selection, but this amount of sources and roughly their locations are known. We actually want to compare to those methods and see how sensitive are those to mistakes in the prior knowledge compared to our method, which doesn't really assume prior knowledge, just at least 2 targets. Yeah. With that, I want to thank you for your attention.
Thank you. So questions from the audience and from online?
Hello, thank you for your presentation. And I have a question about your optimization problem. Can you back to up?
One more?
Yeah.
Where
The original optimization problem.
Original?
Yeah, yeah.
Not this one?
This is an NP graph reformulation. Yeah, this one. This one. Can you extend it to multiple targets? I mean, it's more than 2 targets, because in your case, it's just a 2 targets.
Yeah, actually, the Cramér-Rao expression here, this is for an arbitrary number of targets. So yes, you could. I mean, it's really only here where we say there's only 2 targets. So you could do it for more, but then the trick that I showed earlier, where it only depends on the difference of angles of arrival, you don't have that anymore. But yes, you should be able to, in general, you should be able to do this problem for more than 2 targets. It's just that I'm not sure how you would solve it if you don't also know the target positions. So.
Okay, and how do you define the selected antenna number M in theory?
The M?
Yes.
Yeah, I mean, that's an input parameter. So actually, yeah, last week I saw a poster presentation on minimum amount of sensors needed to get some performance for an X number of targets. You could use a method like that to determine how many sensors you expect to need. In general, actually, when we were writing this, what was in the back of our mind for M was power constraints or cost constraints, just in terms of how many front ends can you buy. That's the number of sensors you can select, essentially. So we were mostly thinking about money.
And do you put some constraint for the sparsity? Because you just use you just have one constraint.
Yeah.
It means the location of the selected antenna it's not known in the ones. So maybe you just choose the middle part of the array, but this will reduce the aperture of the array. Do you?
Yeah, we've always seen that the area aperture is always maximized as a result of our optimization, actually. So the elements furthest apart from each other will always be selected with this method as far as we've seen. So
Okay, thank you.
yeah, and in terms of the sparsity, I mean, originally, yeah, this was an L1 norm less than equal to M. I mean, adding antennas is always better, and P can only be positive, so it's just the sum over P that's equal to M. It originally started as a sparse array problem. It's just you don't really need that formulation in that sense. How most people do sparse with L1. Thank you.
Any more questions? Yeah, the back.
Just had a question. Are all the sources equal power?
Yeah. Yeah.
So any idea how the design would change if one is stronger, one is weaker?
Well, I think in that case, it would be very obvious which one would be the worst case. So that's actually also why we chose to do equal power, because otherwise we would just have to say, okay, we would still have to put a limit on how much more powerful one can be than the other. And actually the biggest difference in power between the two will always produce the worst case. So, but I don't actually have concrete results for what the difference is in that sense. It's just that we didn't really know how to set that limit and if it made sense at all. So we wouldn't be able to explain that limit. So that's what we chose for equal power. Thank you for the question.
Yeah, I also have a question.
You have a question? Okay.
So I guess here, all of the math that you don't realize on the fact that you are in the far field.
Yeah.
And so this allows you to have some kind of invariance that allows you then to only rely on the difference between the two targets.
Yeah.
But
exactly.
if you were in the near field, do you think that the optimized array that you have generated would change dramatically? Or you think that that kind of shape would still remain?
I mean, gut feeling, I want to say no, but brain feeling, I have no clue. Actually, no, this is a very good question. That's I want to look at that right now. So thank you. Yeah, no, I don't know what else it would turn into. That's kind of the thing, but I also don't have any good reason to say that it shouldn't change. So I don't think that's a very satisfying answer, maybe, but I'm glad for the question.
Any more questions? If not, let's thank Costas again.
Thank you.